Yeah, welcome again to another video. All right, so this is another question we have. Okay, we have another question here on electromagnetic waves. Okay, I think after I made the first video, so the question was sent to me online. So, anyways, the one that was given to me was this particular one. So, we're going to, anyways, I've done this question before, so I'm going to be, I'm going to be solving it again in this class. I mean, yes, in this tutorial. So, but the first question we have here reads, in which region of the electromagnetic spectrum is radiation of wavelength 50 micrometers? Now, the first one was all about, the one I did in the first video was the one about frequency, okay? Now, we want to know in which region of the electromagnetic spectrum can we have a frequency, a radiation of frequency 300 megahertz. That was the first question. But now, this is when we're giving wavelengths, because the question I was asked is, okay, what if it is now wavelength that we are giving? How do we find out the region in which the radiation, okay, the radiation lies, in the electromagnetic spectrum? All right. So now, for this question, what we need to do is to convert the unit, to convert this wavelength. Now we're giving this wavelength the radiation of wavelength. So that means the wavelength of the radiation is given to be 50 micrometers. And we know that 1 micrometer, okay, 1 micrometer will be what? 1 times 10 raised to the what? Power of minus 6 meters. Okay, so which means we have to what? We can then write this micrometer as what? As 10 raised to the power of minus 6 meters. Okay, now when we have symbols like this in physics, they are called prefix. We have the commonly used prefix, in physics. One of them is micro, milli, tera, hexa, yocto and yacto, okay, and many others. All right, so in this case, we have 50 micrometers, and these 50 micrometers, okay, can be what? Can be written in standard scientific units, scientific notation as 50 times 10 raised to the power of what? 10 raised to the power of minus 6 meters. So which means the wavelength can now be what? 5 times 10 raised to the power of 1 minus 6 meters. So the wavelength, okay, would then be 5 multiplied by 10 raised to the power of minus 5 meters. Now, we have the wavelength to be 5 times 10 raised to the power of minus 5 meters. So which means the order we have here is what? Negative 5. That's 10 raised to the power of minus 5. Now, this will lie in the infrared region, because the infrared region, okay, have its wavelength, okay, in the order of 10 raised to the power of minus 7 to what? 10 raised to the power of minus 3. Okay, so now, like I said, now this wavelength, okay, this wavelength lies in the infrared region. Okay, it lies in the infrared region. Okay, it lies in the infrared region because now we know that because it ranges from the infrared region wavelength. Okay, now it ranges now. What I mean, I'm using objective pronoun here. It ranges, that means the infrared region ranges from 10 raised to the power of minus 7 to what? To the 10 raised to the power of what? Minus 3 meters. So this lies in the what? Infrared region. So that's for question number 1. Now for question 2. Now let's have our solution for question 2. We have a narrow beam of an unpolarized light. We know what that means. Unpolarized light, because we know that when we talk about polarization is a confinement of wave. Okay, confinement of wave, so that they can travel, okay, they can travel along a what? A plane. They can travel along a plane. and they have their vibration, that's their direction of propagation or vibration to be what? To be perpendicular to the direction of propagation. So in this case, so we have unpolarized light. So that means the light is not travel in a plane. Now, is incident at the boundary between air and glass. So the first medium is air, the second medium is what? Glass. Okay, the figure below shows the incident ray. We have the incident ray. This is the incident ray. Now, the angle which the incident ray makes with the normal, this is the normal ray, is 56.3 degrees. Okay, then we have the reflected ray. Okay, now we also have the what? The refracted ray. This happened in the case of refraction of light. Light will be partly reflected and what? Partly refracted. Okay, so in this case, so now when the light is incident, okay, at the interface separating the air and the glass boundary, okay, or separating the air and glass, so we have the angle which the incident ray makes with the normal to be 56.3 degrees. Okay, now the angle which the refracted ray makes with the boundary is theta. Okay, this is not the refracted angle. This theta is not the refracted angle. Okay, but it is the what? It is the angle which the refracted ray makes with the what? With the boundary. The boundary is, the boundary between the air and glass. Now, the refractive index of air is 1.0, okay, and the refractive index of glass is 1.5. So we want to calculate the time taken for the refracted light to travel a depth of 6.0 centimeters. 6.0 centimeters. So that means that the light travel vertically through the glass, okay, at a distance of 6.0 meters. That's what it means. Okay, now, so if the light travels vertically through the glass at a distance of 6.0, 6.0 meters, that is the normal ray. Okay, but here we have that we should calculate the time t taken for the refracted light to travel a depth of, so that means that if the light can travel a depth of, a depth of 6.0 centimeters, okay, 6.0 centimeters. So then we need to find out, the length of this line. Okay, we need to calculate the distance. That's, the refracted ray. Okay, the distance covered by the refracted ray. So when we know the distance covered by the refracted ray, then we now again calculate the speed of light in the glass. So when we know the speed of light in the glass, then we know that then in uniform motion, okay, we know that velocity can be expressed as distance over time, or can be given to be what? Distance over time. So we're going to use that to obtain the value of time t. All right, so let's get into the video now. Like I said, so what we have here, we are given the index of refraction in air. The index of refraction in air is 1.0. Okay, we're also given the index of refraction in glass. So the index of refraction in glass is given to be 1.50. All right, so now so we are given the angle of incidence. Let's say angle of incidence is θ1, and that is given to be 56.3 degrees. Okay, let me get my calculator. Okay, 56.3 degrees. Okay, we have 56.3 degrees. So we need to find the refracted angle. Okay, the angle which the refracted ray makes with the normal. So let's represent that with what? θ2. Okay, when we know the refracted angle, then this other angle will be what? Known, because we know that the normal ray, okay, the angle which the normal ray makes with the boundary is 90 degrees. So when we know the value of this angle, we can actually subtract this value from 90 to get the value of this other angle. All right, so we want to find out what is θ2. Let's find out what is θ2. Now we know that when we have all these values, okay, and we want to calculate the value of θ2. So to calculate the value of θ2, then we'll have to employ the use of Snell's law of refraction, which I explained in one of my videos. Okay, that's the ratio of the sine of angle of incidence, okay, angle of incidence to the sine of angle of refraction. okay, will be proportional to the what? To the reciprocal of the absolute refractive index of medium 1 with respect to medium 2. Now, what we call absolute refractive index, because now somebody asked me what is the difference between refractive index and absolute refractive index. Now, for refractive index, we define refractive index as the speed of light in air with respect to speed of light in what? In a material. Or we can have the wavelength of light in air with respect to the wavelength of light in a material. But when it comes to absolute refractive index, it will now be the ratio of refractive index of one medium with respect to what? Another medium. All right, so we know that using Snell's law, using Snell's law, we know that N1, we know that this is already N1 sine theta 1 equals to N2 sine theta 2. So we want to calculate the value of theta 2. So we are going to have N1, when we rearrange this equation, we have N1 sine theta 1 over what? Over, we want to calculate the value of sine theta 2. Okay, so we can express this as the inverse sine of N1 sine theta 1 divided by N2. Okay, divide by N2. So this is theta 2. So we can then say that theta 2 will be equals to the inverse sine of, now N1 is air. Remember, the first medium is air. Okay, multiply by sine, sine angle which the incident ray makes with the normal, which is what? 56.3. Okay, 56.3 divided by, now we have the refractive index of the glass to be what? To be, remember, this is glass. Okay, why this is what? Air. So the refractive index of the glass is 1.5. That's 1.5. Okay, now first let's find out what is sine 56.3. Okay, sine 56.3 would be, so we have theta 2 to be equals to the inverse sine of 0.83, okay, 0.83195 divided by 1.5. So theta 2 will be equals to, so when we divide this value by 1.5, then we're going to have, we are going to have our sine, an inverse sine of 0.5546. So now let's get this inverse sine of 0.5546. Now that would be 33.68. So the angle of refraction, okay, angle of refraction will be 33.68. 33.68. So this is our angle of refraction. That's our angle of refraction. All right, so we have our angle of refraction. Now, well, we'll get there. Okay, so what we have here is, now we want to calculate the time t taken for the refracted light to travel a depth of 6.0 centimeters. Okay, that means, remember I said the light travels, okay, the light travels at a depth of 6 centimeters, but the length of this line, now we have our theta 2. Okay, we have our theta 2, which is the angle of refraction. Okay, now what is the length of this line? Because when the light passes through the glass, glass is a transparent material, you understand? So which means the light will pass through the glass. So the length of this line, so we need to first calculate the distance traveled by the refracted ray, not the we know that when the normal ray, okay, strikes the boundary separating the two media, okay, symmetrically, okay, now we know that that's between the boundary, okay, to the what, to the the glass, you understand, it passes through the glass. So the light passes, straight through the glass. But now, so from where the light enters the glass to where it emerge. Okay, the distance is 6 centimeters. So we have this to be the distance to be what? D. So we already know the value of theta 2. So now to be able to calculate this, then we apply the Pythagoras theorem. So this becomes the adjacent and this becomes the what? Hypotenuse. So this is angle theta. So which means we're going to have cosine of angle theta 2, which is this angle. All right, multiply then adjacent over hypotenuse. We have adjacent over what? Hypotenuse. So we have cosine of angle theta 2, okay, equals to the adjacent is now let's change the value, let's change it into what's it called? Let's change it to, okay, cos theta 2 is 33.68, which is equals to the adjacent is 6 centimeters, which we are going to convert into meters. That will be 0.06 divide by d. So when we rearrange this equation, we are going to have d to be equals to 0.06 divided by, now let's get the value of cos 33.68. Now, what is the value of cos 33.68? Okay, that will be 0.8321. We have 0.8321. All right, so now what is 0.06 divided by 0.8321? Okay, 0.072 meters. That's the distance. Now, we want to calculate the time t taken for the refracted light to travel a depth of this 6 centimeters of the glass. Now, remember in my previous video, okay, now this is important. Okay, so remember we now have the distance. Okay, we use Snell's law. So using Snell's law, then we are able to get the value of angle of refraction. Okay, now we now have the value of the distance, okay, the distance traveled by the refracted ray. So we know that velocity of glass is 2.0 times 10 raised to the power of 8 meters per second. Now we did that in the previous video. Okay, so we want to calculate the time taken. So we're going to use one of the formula in uniform motion, which is velocity. We know that velocity is what? Distance over time. So we have the distance, then we're looking for the time. So which means we're using v equals to d over t. And we know that t, okay, we have using v equals to d over t. So we have t to be equals to d over v. Okay, d over v. Don't forget, this is the velocity of glass. So time t will be equals to the distance, this value 0.072 divided by the velocity of glass. All right, so now we have the speed of light in glass, and I said we are going to use the formula for calculating velocity from uniform motion. So we know that in uniform motion we have that velocity is distance over time. Okay, so which means from here we are going to have time to be what? To be distance over what? Velocity. Distance over velocity. Now, this is the distance. So to calculate the time, we are going to write, the distance is 0.072. Okay, then we divide it by the velocity. The velocity of glass is 2.0 times 10 raised to the power of what? 8. Now the unit of time is the seconds. The unit of time is the second. So here, now let's do it this way. Let's say let's do it as 0.072 divided by 2. Okay, that would be 0.036. 0.036. So we have 0.036. Okay, now if you have to bring this 10 raised to the power of 8 to the top here, we're going to have multiply by 10 raised to the power of what? Minus 8. And that will be minus 8. The unit of time again, remember it's what? Seconds. So time t, okay, time t will then be, so we have to what? So let's write this in standard scientific notation. So we have to move this, we have to move the decimal point. So that will be 3.6. Okay, that will be times 10 raised to the power of minus 2 times 10 raised to the power of minus 8. So when we combine the powers of 10, okay, we then have our time t to be 3.6 times 10 raised to the power of what? Minus 10. That will be minus 10 seconds. So this is the time, okay, this is the time t taken for the refracted ray, okay, to travel a depth of 6 centimeters of the glass. Bye bye. Thank you.